Hello, I'm Saheb Bansal, a student from the automobile branch here at PDEU, and today I'm going to be explaining the concept of carbon fiber monocoque chassis. A monocoque chassis is the basic structural component which provides both structure and shape to the vehicle. It can be compared to an egg for better understanding, where the eggshell provides us the structural rigidity as well as providing the shape to the egg. Before the use of monocoque chassis, the vehicles were divided into two basic components: the frame and the body, which was mounted upon the frame. The frame provided the basic structural rigidity, and the body provided the shape of the vehicle. But a monocoque chassis does both jobs at the same time. A monocoque chassis supports both tensile and compressive forces within its perimeter, and it can be recognized by the absence of a load-carrying internal frame. Moving on, carbon fiber reinforced polymer, or carbon fiber reinforced plastic. It goes by many names. It depends on its particular properties or the composition of it. It is referred by different names. It is basically an extremely strong and light fiber reinforced plastic, which contains interwoven carbon fibers with a sheet of different polymers. It can be plastic, it can be ceramics. It varies depending upon its usage, where it's going to be applied. Uh, carbon fibers. Carbon fibers are definitely expensive to produce, but they are utilized in industries such as aerospace, superstructures of ships, automotive, civil, it is also utilized nowadays in highly professional sports equipment where lightness and strength goes hand in hand. Uh, all of these industries nowadays value the strength to weight ratio to the upmost level, because you need the you need the utmost strength while being as lightweight and optimized as possible, and carbon fiber definitely fills that void. If we compare a structure of aluminium and carbon fiber with the identical dimensions, the weight reduction in carbon fiber is so significant you can literally feel it in your hand. You don't even need a scale. It might be even more than half of that of the aluminum structure. And further moving on, this is a basic timeline that I've curated, where it shows, first of all, in 1879, Thomas Edison used carbon fibers as testing metal for the filaments in the early light bulbs. Then, in 1958, Roger Barron accidentally produced the first petroleum-based carbon fibers. Then, to make it more feasible in Japan, Dr. Akio Shindo uh, made it much more feasible and possible for carbon fiber to be produced in industries by inventing a organic polymer resin which could bond the different carbon fiber weaves together, and made a production method. And then further on in 1963, the British scientists W. Watt and Ellen Phillips and some more scientists patented a carbon fiber manufacturing process, which then Rolls-Royce utilized in their engine development program for their lightweight engine blades. In 1971, the Citroën SM offered its first carbon fiber wheels, and Carbon fiber wheels are important because they reduce the unsprung mass of the vehicle. And basically, to understand easily, the less the unsprung mass, the less the suspensions have to work to handle the undulations faced on the road. So basically, the suspensions have to work have a much easier work at handling bumps, and that produces a more comfortable ride for the passengers. Then the legendary McLaren Honda, which was, of course, driven by Ayrton Senna from F1. It was developed by Honda. The Monocoque chassis was made entirely of carbon fiber reinforced polymers. Then in 1990, the Jaguar XJR 15 was the first production car to be featured with a entirely carbon fiber monocoque frame. And nowadays, 2021, where energy efficiency is so prioritized, we need lightweight materials. So almost every industry nowadays utilizes carbon fibers, such as automotive, sports, aerospace, aviation. They all prioritize energy efficiency and weight to strength ratio. So nowadays it's really become more widespread. Why do we use carbon fiber instead of other metals? Let's see ahead. The fourth, magnesium being the fourth most common element, it's not as easy as simply mining it in order to create materials for automotive manufacturing because, as you all know, due to its chemical properties, it spontaneously ignites with oxygen, and it can be very hazardous if used in its raw form. So it needs to be combined with other elements like diposium and ytterbium to provide better strength to be used in a car parts. It can result in a higher cost. So basically, it's even though it's a common element, it needs to be processed further to be utilized, and that increases the price. For the same tensile strength, aluminum will be lighter than steel but also costlier. It is much harder to recycle than steel as it must be separated into different grades before melting, meaning repairing and replacing the damaged parts can be complicated and costly process. And furthermore, for titanium, it is significantly stronger than steel, but mining it is a very very complex process since and machining it as well, because for machining titanium you need even stronger tools to form the titanium, because it won't even budge if you use steel or normal aluminum tools. So it is time consuming. You need much more expensive tools to work upon it. And if in case of an accident, it being a very strong material, the titanium splinters are very strong and they can be very hazardous. Next, the pros of using carbon fibers in monocoque. Nowadays, monocoque chassis are widespread in high-end luxury cars or even mostly the newer, as you can see in Teslas or Lucid Air electric vehicles, where the lightness and the strength of the vehicle depends upon the structure, basic structure, and the monocoque chassis, if made from carbon fiber, it can significantly reduce the weight. And by reducing the weight, you can fight the you can increase basically you can increase the range of the vehicle. And we know the term range anxiety that has been coined recently because of the fear that your vehicle will get discharged easily and you'll be stuck on the side of the road. So to fight that, we can use lighter materials to increase the efficiency and in turn increasing the range of the vehicle. Next, the strength consideration, as we all know, as I have explained earlier, that carbon fiber has excellent strength to weight ratio. So it can be used in smaller quantities while providing great structural rigidity to the vehicle. It even has a good resistance to creep as it has a very high yield point compared to other metals, in turn giving it incredible durability, thus reducing the susceptibility to fatigue failures. And it also helps in providing dampening solutions to reduce the vibration found in vehicles. It can reduce the vehicle's weight by more than 60% without compromising passenger safety or integrity of the part, because you're not compromising strength for lightweight. But if you try to be lightweight and do weight reductions in a vehicle or a chassis made in completely of metal, it can prove to be as that we're adding more weak points in the structure, and that can result in uh, more collapsible zones in the crash scenario. Environmental effects: it does not it does not corrode like other metals and has high temperature resistance. So as we have seen, if a vehicle which is if made of steel or iron or other metals, they can easily be corroded if they're uh, stored in some humid conditions. For example, a city like Mumbai, so they need to be prepared, like galvanizing, or they need to be painted with some special anti-corrosive paints. But carbon fiber does not have that issue. In vehicle dynamics, the vehicle dynamics is basically the art of the study of uh, the study of learning the vehicle's dynamics, basically how it reacts to to the road, or how does the driver perceives the road while driving the vehicle, how it reacts to the vehicle, how the driver input comes results in the vehicle output. So in corners, a carbon fiber vehicle will flex meaning less than a steel or aluminum, meaning that the torsional bending of the chassis will be reduced more than I think 70%, because of steel and aluminum being ductile metals. This keeps the wheels planted in firmer onto the ground, increasing traction and speed. Because in vehicle dynamics, you need to keep the wheels in contact with the ground. Otherwise, if the tires won't be in contact with the ground, uh, it would be hard. It would be much harder to control the vehicle. So for the driver to have utmost control over the vehicle, the wheels need to be remained on the ground. If the chassis does not flex, that makes it possible. So these were the basic pros of carbon fiber monocoque. Moving on, the challenges and advancements. The most grievous challenge is the just a small portion of carbon fiber reinforced plastic scrap is recycled. In 2015, according to data, more than $300 million worth of carbon fiber was discarded in landfills. Companies such as Adesso Advanced Materials, Conora Technologies, and Malinda are solving the problem by developing purposefully recycling resins of pre-packed content. Adesso also created an amino-based curing agent that allows for fiber recovery, and Conora also makes reversible cross-linkers, uh, and Malinda's resin system allows for depolymerization, allowing for cradle-to-cradle life cycle, which means it can be reused. So work is being going on, but it takes time. Furthermore, a 3D scanning method shows promise, but it needs further progress as well as additional sorting technologies. Zartec is one company that has developed recognition technology that uses 3D image processing and deep learning to enable users to recognize mechanical parts. Nonetheless, recycled CFRP has low performance characteristics when compared with virgin materials, though innovations in preserving fiber length and aligning fiber orientation may lead to improvements. The other one is the cost. The carbon fiber's high cost has been a huge barrier to its widespread use as solid stiff reinforcement for advanced composites. Researchers at the U.S. Department at Energy Oaks Ridge International National Laboratory have demonstrated a manufacturing process that they predict would reduce the cost of carbon fiber by 50% and the energy use of its production by more than 60%. The success of researchers could speed up by the adoption of carbon fiber composites in high volume industrial applications such as automobiles, wind turbines, compressed gas storage, and infrastructure. Last year, ORNL made the new method available for licensing after thorough research and effective prototyping by industrial partners. So, if the widespread use of carbon fiber is uh, encouraged, it will encourage other manufacturers to invest more time and money in their own carbon fiber R&D, and hence reducing the overall cost of carbon fiber production. So, to conclude, in comparison to metals, carbon fiber reinforced composites are becoming more competitive and cost efficient. CFC components are more expensive than metal components at the moment. The cost of composite design and production and assembly techniques. These innovative developments would significantly lower the cost of composites, resulting in an exponential increase in demand for two composites in the coming years. Composite design, research, and manufacturing tools can assist in reducing engineering cycle time, lowering costs, and improving quality while retaining component repeatability. Uh, Here are the references that I've referred for this presentation. And thank you. That was all from my side.